connections with a safety moment. And it seemed to me in the current climate, it's important to remember a message that I remember being told as a child. It came from a poster that's probably older than me, but still equally true today, that washing our hands is really important to keeping ourselves and our loved ones safe, be that in the current environment with COVID-19, where many of us in our professional lives visit wastewater treatment plants, or when we're at the home of the office. Taking the couple of minutes to wash your hands is a great way of keeping yourself safe. So what are we going to talk about today? Looking to cover a number of things. The first one's a little bit of wastewater history. We're then going to go and talk a bit about wastewater treatment and a couple of the things that certainly I'm finding exciting at the moment and really moving us in the circular economy direction. We're then going to talk about the various parts of the resource recovery plant, reuse energy and nutrients. And then hopefully we'll have a little bit of time at the end for questions and discussion. So let's start off with that wastewater history. I know this history is biased. I'm telling it from the perspective of somebody sat at his home in the UK. If I was telling this story from America or India or China, I think some of the facts I picked up might be a little bit different, but the fundamental basis of it would be very much the same. I think if we look, the growth of cities and international trade has got an awful lot to answer for in terms of human health. Bringing all those people together in one place is not only good for people, it's good for all the things that like to live off people as well. 1831, 1832, cholera arrived in the UK on board ships. 32,000 people died in 1831-32. About 13,000 in London. At that time, the population of the UK was about a quarter of what it was at the moment. So that's equivalent to over 120,000 people today. So certainly more than the current epidemic. Came back again in 1849. Another 14,000 people died. At that time, people really had no idea where something like cholera was coming from. The whole of London stank. People, when they built the city, regarded the river as pretty much a convenient place to throw anything they didn't know what to do with, including all the human waste. So we had a dreadful stink or miasma arising from it that people thought was what was making the meal. In 1854, John Snow proved the link between water and cholera in a famous piece of work by looking at a pump in London, proving that all the people who'd become ill around it had drunk from the same water pump. The first thing that was done to sort that out was by a guy called Basil Getty, and he solved the problem by building sewers. And he built sewers through the centre of London and took the flow of wastewater out to the east of London, built some big tanks and released it into the Thames on a falling tide, so it was taken out to sea. And if any of you've been lucky enough to visit London and walk along the banks of the Thames, if you walk along the embankment looking in the river, what you're actually doing is walking along the top of Basil Getty's sewer. So that and other actions have really had an impact on human health. I mean, this is looking at what's happened to the death rate in the US over the last 100 years. And you can see that it has dropped dramatically over that period of time. And I think the same is true of most other countries in the world. And certainly I'm very proud to say that as a wastewater engineer, I and my colleagues have done our piece for improving the human condition this way. So again, in the current climate, it's Certainly worth noting the 1920 influenza pandemic and the effect that had as we sit here now contemplating COVID-19. Certainly pandemics have a huge effect on human society. So we talked about Basil who took it, basically moved the stuff away and got rid of it on the falling tide. We moved on from there to start developing treatment. In the late 19th century, we saw the development of percolating filters. The document on the left, something I'm particularly proud of, that in my office at work, I have a series of original patents by Frank Candy, who was one of the proprietors of one of the companies that ultimately came together to form Black Veatch. And this is a patent for improvement in precipitation tanks and the means of delivering water to filter beds. So direct link I have back to some of this original treatment work. Beginning of the 20th century, the UK Royal Commission sat. Took them 14 years to come up with their recommendations on disposal. Seems a long time, and I can't imagine something going on that long today, but did a very good piece of work. And you may have heard of Royal Commission standard, which set a standard for treatment that still gets talked about today 100 years later. So might have taken them a while, but they did a very good piece of work. Arden in Manchester, Davy Hume developed activated sludge back in 1913. And that really set the scene for modern wastewater treatment. And the combination of attached growth in percolating filters and suspended growth in activated sludge is what we've been working with ever since. At the same time as protecting human health, we've also been protecting the environment. So moving a bit further forward in time, certainly this event was in my lifetime. And it's the Kayakawa River Fire of 1969. At that time, this is up in Cleveland, which is in the Rust Belt in the US, and lot of industrial activity, a lot of oil floating on the river, and that occasionally caught fire. And in 1969, this caught fire and grabbed the national attention. This photograph appeared on the cover of Time magazine in 1969, and this is really part of the pressure that led to the formation of the US EPA and the passing of the Clean Water Act. So one interesting side note on this is we all think that fake news is a relatively new event, but when the fire took place in 1969, it was a fairly small event, and the local fire brigade had got the fire put out before any of the press arrived. So some enterprising journalists dug back in the archives and found a photograph of the 1952 river fire, stuck that on the front of Time magazine, and that was the pushing forward. Whether that's fake news or not, I'll let you decide. So we said the basics nearly 100 years ago, but ever since then, we've been evolving the technologies from the trickling filters through activated sludge, things like MBRs, MBBRs, and I can't work for Black Veatch and not also put in a plug for my good friend and colleague, James Bernard. James invented biological phosphorus removal probably 50 years ago now. It's become a mainstay of treatment. He's still now 80 years old and still churning out amazing new ideas. So, great pillar of our industry. I thought I'd share with you a couple of recent innovations that Black Veatch has been pleased to be a part of. The first one is enhanced biological phosphorus through sidestream biological phosphorus removal. any of you who've been involved in biological phosphorus removal plants will have found that sometimes they work really well, and sometimes they can be really difficult to get going. And over the years, we've been looking at this, and we discovered there's influent conditions that make biological phosphorus removal work well, and influent conditions that make it work badly. And that your influence can change over time. So you can have a plant that's working really well. You can have a industrial discharger in the catchment who shuts down, stops discharging, reduces the amount of VFA that's available in the influent, and the quality of your phosphorus removal will decrease. The other thing that's well known about biological phosphorus removal is it can be susceptible to wet weather interventions, so that if you get a storm event, it can wash your biomass through the system, and it takes quite a while for the plant to recover. So what James has been thinking in the recent years is that if you can decouple your anaerobic sludge retention time from the mainstream hydraulic retention time, you get some significant improvements in performance. So the approach we're taking to that is to enhance fermentation in an anaerobic zone, target some really deep anaerobic conditions, ORPs of minus 300 millivolts, limit the mixing energy, and that's proved to be an interesting challenge for engineers who love to put mixers in and keep everything churned up and think they're doing a great job. And also limit the flow of influent into the anaerobic zone. We've had success with this in really 3 different configurations. The first and simplest approach is to just turn off mixing in one section of conventional B&R plant. So in one of the aerobic zones, turn off the mixers for 23 hours a day. We do this, for example, at Henderson in Nevada, and the plant's use of auxiliary chemical for phosphorus removal stopped almost overnight. The second way of doing it, which allows us to get the benefits of the independence from peak flows, is to put a side stream fermenter in. So take a proportion of the flow that's going through the anaerobic zones, put that into a side stream fermenter. Again, deep anaerobic conditions, return that flow. Again, at Cedar Creek, we've done that and seen really good results. And the third approach is actually to ferment the RAS. So pick up the return activated sludge that's leaving the clarifier, put a 1 to 4 hour tank in there, ferment it in there, and put it back in. And all of these we found have given us great improvements in the consistency and quality of the phosphorus removal. So this is great, and we're looking to advance this in the industry, and we're very pleased to say that we're currently working on a Water Research Foundation research project focused on writing some guidelines for how to do this successfully. We've got 21 utilities participating in this work globally. We've got a research equivalent of $1.3 million of effort. This effort was identified by Water Online as one of the top 10 innovations in 2020. And Dr. Liam Browning of Black Veatch is leading a team of international experts in producing these guidelines. So why do we care? Well, because we think it can, by moving the selective pressure into the side stream reactor and getting these deep anaerobic conditions, we can make a big difference to how we design plants. So for new plants, for example, when we applied this approach at Rock River, the capital that was required to upgrade the plant about halved, so that was a major advantage for that city. And on conventional treatment plants, You can get much better performance and more stable performance. So clean water surfaces, for example, saw a significant drop in the effluent phosphorus in their plant when they took this approach. And the other big advantage for utilities is the reduction in chemicals. By moving away from having to dose continuously ferric to maintain phosphorus removal, that can be a big saving in operating costs. And also, if you look at the carbon impact of that chemical, it's a reduction in the carbon footprint of treatment as well. Example of a recent plant that we commissioned about 18 months ago, Wakarusa, which is relatively close to our head office in Kansas City. A nice, neat little plant. It's got the fermenter is one of the tanks you can see in the foreground there, and that has run consistently at less than 0.6 milligrams per litre, total phosphorus 0.3 ortho, with no downstream filters after the secondary tanks and no chemical addition. Very nice, neat little plant. The other technology I think I thought I'd bring to your attention is membrane aerated bioreactors. We in the wastewater industry are great, like so many people, at the 3- and 4-letter acronyms. So MABR, not to be confused with membrane bioreactors, or MBR, or moving bed bioreactors, MBBR. Less complicated. Black Veatch tries to advance technology like this through something we call the innovation platform, where we bring collaborators in to work together to advance the industry knowledge. And this particular piece of work was done with the city of Hayward in California and Suez Environmental. So what is an MABR? Well, in some ways, the actual material looks quite similar to an MBR. So you've got a series of membranes, either in the form of hollow fibers that look like a bit like hair, or in terms of flat sheets. The difference to an MBR is, in an MBR, the water flows through the membrane. So you'll keep the mixed liquor on the outside. The membrane will act as a separation. The water leaves through the membrane. In an MABR, there is no water inside the fiber or inside the sheet. You blow air on the inside of the membrane. The oxygen diffuses through the membrane, and you get a biofilm growing on the outside of the membrane. That gives you really a quite unusual set of conditions, because on the surface of the membrane where the oxygen is going through, you've got highly aerobic conditions, and aerobic reactions can take place with the biomass. In the bulk of the liquid that these membranes are suspended in, you've got anaerobic conditions. And so a whole series of biological processes are possible in the same tank. So what does the MABR give you? It's a bubbleless aeration device, which means you can get very good control of the air. Just controlling the flow of air into the membrane directly controls the amount of oxygen going into the system. Because you're not blowing bubbles through a tank, you also don't have the potential to blow VOC off the top or create foam. And because it's a biofilm technology, you get the advantages of other biofilm technologies: intensified treatment, small footprint, lower sludge production, and greater resilience to slug loads or toxic events. Again, what's the proposition? Well, as I say, you've got aerobic and anaerobic conditions present in the one tank, which means that you can actually do all the processes of total nitrogen removal in the single tank. So you can oxidize ammonia to nitrate on the surface of the membrane where there's high levels of oxygen, and then reduce that nitrate back to nitrogen gas further out in the biofilm. That gives you the ability to potentially retrofit this to existing processes. So we think it's a great solution where you need to get more treatment out of the same tank, and rather than having to build new concrete tanks, can retrofit membrane racks like this and get more capacity. You get better oxygen transfer efficiency, can reduce recycle pumping, and also can potentially avoid having to add a carbon source to get nitrification, which again can be a very big cost and a big carbon impact. We aren't providers of these membranes. There are three main suppliers out there at the moment: Fluence, Suez, which call their product Zelong, and Oxymem. We actually worked with Suez and Hayward to demonstrate this at the Hayward facility. And this is the pilot plant you can see in the photograph. The reactors were in the right sort of stainless steel box you can see on the right hand side, and the rest of the skid was instrumentation and backup. And you can see the biofilm growing on the membranes in the picture on the right hand side. We opened it up to check it out. These are some of the results from the pilot testing. So we started off looking at suspended solids retention time of 0.3 days, which is incredibly short compared to conventional treatment. And we got some removal of nitrogen even under those conditions. When we got to 3 days, suspended solids retention, which is the sort of point that you'd normally not be considering nitrification to take place, we're starting to get significant reductions in both ammonia and total nitrogen, so achieving a pretty high level of treatment. We also, having run them at fixed rate, also simulated diurnal flows to see what happens. And here you can see that 3-day suspended growth retention time. The top blue line is the incoming ammonia. The yellow line at the bottom is the ammonia, which is almost nothing. And you can see the nitrate level, which in this case is pretty much all of your total nitrogen, pushing along at around the 10 level. So a pretty impressive set of treatment at a very short retention time. And certainly that's a technology we're really excited about and think it's going to make a very big difference. I guess having talked about the treatment, we should talk about biosolids. I could spend an hour very easily just talking about biosolids, but I'm not going to. I thought I'd just make a few general observations. The first one is we've been making biosolids pretty much as long as we've been treating wastewater. I say no sign of them going away. And a lot of the challenge of biosolids is not the material that comes from human waste, it's all of the other stuff that ends up in our sewers. So heavy metal contamination, organic chemical contamination, all of those tend to end up in the biosolids, and we have to consider them for disposal. There really is only two options for dealing with biosolids. One is to dispose of the organics, and certainly the circular economy approach to that is land application and putting those organics back onto the land as a soil improver. It's also possible to dispose of those organics to landfill, and certainly in the old days we also used to dispose of it in terms of sea dumping, though I'm pleased to say we've pretty much stopped that globally. Normally before the organics are disposed of, they'll be pre-treated, form of digestion, composting or drying. The other side, if you don't dispose of it, is to try to destroy the organics. So basically convert the organic compounds to carbon dioxide. There's a number of things that are used for doing that: incineration, gasification, supercritical wet air oxidation, chemical biological destruction. Most of those are pretty intensive processes. The one thing you can say about pretty much all of these is that if you try to put a plant in like that, you can get some pretty strong public opposition. And there can be pushback on any of these. My personal solution is that everybody should get an annual delivery. This is your share, do with it as you will, but unless we can manage to do that, which I think is politically totally unacceptable and not really a serious suggestion, we're going to have to find a means of dealing with it. And the challenges keep coming. We think we've got a new technology or something that gives us a great result. Two of the things in the last probably 12, 18 months I've seen really arising and getting some serious consideration are perfluoroalkyl and polyfluoroalkyl compounds, known as PFAS. If any of you haven't come across PFAS, this is a byproduct of firefighting foams, non-stick liners, and a whole pile of other modern world compounds, which have been now demonstrated to contaminate groundwater in many parts of the world. Started off being typically found around Air Force bases and things like that, where there's a lot of firefighting foam being used, but also now being found elsewhere. And most recently have been found in biosolids, and there's a big debate in the US at the moment about what's the significance of that and what is the consequence for human health. The other one we're starting to see quite a lot of attention to is microplastics. And certainly research has now shown there is definitely microplastics in biosolids. There's definitely a buildup of microplastics in soil that's had biosolids applied to it. The real question is, what's the impact? And I think it's quite interesting that it looks like the source of most of those microplastics is clothes washing. That when you wash clothes that contain man-made fibers, lengths of those fibers break off and gets discharged in the water from the clothes washing, and that finds its way into biosolids. But I do think as we consider all these things, and maybe the easy answer with a lot of this would say, right, let's just go to some form of oxidation and get rid of all this material. But we do need to remember the huge value in the environment of that organic material and make sure that we do get a balance between regulating the stuff we need to regulate, but also making sure we keep taking advantage of that material as a soil conditioner where we can. So let's move on and talk about resource recovery, and probably the first and easiest thing to consider is the water element of that and reuse. Reuse takes many forms, and despite what we often like to tell ourselves, it's not new. So, I think anybody who lives on a long river has pretty much got used to the idea that the water that's extracted for drinking has potentially previously been discharged upstream from a treatment plant. And indeed, there's a very good apocryphal story in the UK that I'm assured is entirely untrue, that if you drink water in London, it's probably been through 5 people already. We've been doing irrigation for many years. And more recently, I think, seems like the world has been standardizing on a reuse scenario that uses MF or UF in front of RO and follows that with an advanced oxidation system to produce water of potable quality. There's plenty of examples of that now around the world. Singapore pretty much led the way with its new water systems. lots in the US and elsewhere. And we're certainly seeing with climate change, water scarcity, and the strange desire of people to live in warm, dry areas, that the interest in reuse in its various forms is growing all the time. I thought rather than talk about the sort of membrane solution, I'd actually just spend a couple of minutes talking about a different approach, which is what can you do if you don't use membranes? And this is the approach that Melbourne Water took about 8 years ago now, looking to produce 880 mLD of reused water from their Eastern treatment plant in Melbourne. Had that gone down the conventional membrane route, that would have been hugely expensive, so they looked to find an alternative for what at the time, and I suspect still is, the world's largest reuse facility. And they spent a lot of work piloting to prove a solution that used ozone, biological treatment, and UV to achieve the level of protozoa, virus, and bacteria removal that their health regulator was looking for. So they did a lot of work on the pilot testing, which Black Veatch were honoured to be able to help them with, doing challenge testing and demonstrating the capability of this treatment. It's now producing Class A plus recycled water for potentially use in irrigation and other uses around Melbourne. So that's a little bit on the technical side. I think it's also worth thinking about what the barriers to reuse are, and they're certainly substantial. I think one of the biggest ones is public perception. I think for very good public health reasons, we have almost an inbuilt concern about wastewater, and it's risky. And when the newspaper headline writers get hold of it, they have a field day. There's lots of opportunities. All the statements on the left are from Brisbane, from the Brisbane Press, when they looked at reuse it about 10 years ago of their drought. An interesting question, particularly if you're going for a dual reticulation system that high quality reused water out, not to be used for drinking, but for toilet flushing, irrigation, things like that. What you do about the cross connection liability issue. If you've got two pipes, one bright purple if you're in Singapore or whatever else it may be, how do you stop somebody either in their own home or a plumber making a mistake and connecting to the wrong thing? And who's responsible if a cross connection gets made and somebody gets ill? Is that the utilities problem? Is that the plumber's problem? Is that the homeowner's problem? And until you get that sorted out, I think there'll be a lot of resistance. And that might sound like a theoretical problem, but I know at least one case in the world where a connection was accidentally made from a recycled water line to the water fountain in a primary school. The water was very high quality and it didn't cause any health issues, but it's a reminder that however careful you are, somebody can make a mistake. But equally, I think, as we think about reuse and what the downside is, then what Benjamin Franklin said 250 years ago is still very true, that it's when the water runs out that we really know what it's worth. And with climate change and population growth, we're seeing that more and more. I guess Cape Town's probably the most recent example of that. So we've talked about water. Let's talk a little bit about energy. There's energy in sewage. Sewage is composed of partially degraded food waste, or poo as my children would have called it. That waste contains energy. If you look at what each of us discharges each day, it's equivalent to about a 20-watt continuous output. So just think of it, we're all bright enough to light up a light bulb. But what we've done historically, we've taken that energy, we've added more energy to treat it. We used to be pretty efficient. I've been to trickling filter plants that actually had no power supply to them at all and achieved their treatment without power. As our standards have tightened, we've had to put more energy in. And as we get tighter and tighter standards and more advanced technology, the energy's been tending to increase with things like MBRs and advanced oxidation with UV. So what are we doing to address that and try and get back towards energy neutrality? Anaerobic digestion, which we mentioned earlier, for stabilization is definitely one of the answers. Again, it's been around pretty much since wastewater treatment began. End of the 18th century, people were digesting biosolids. Hold the sludge 35 degrees C, about 14 days. Bacteria will break a lot of that material down. As a byproduct of respiration, they'll produce a gas that's a mixture of carbon dioxide and methane. In those early days of digestion, the reason for doing it wasn't for energy, it was to stabilize it. The posh way of saying it is to reduce the vector attraction. But what that really means is reducing the smell and the flies and reducing the nuisance value. And if you did this material, it became much more pleasant to deal with, and also reduce the pathogens present in the material, and also reduce the amount of material to dispose of by heading for 50%. But there's also a long history of using that gas for power. So back in 1935, when a new treatment plant was being built in West London at Mogden, that treatment plant included both digesters and an engine house that generated electricity and provided that electricity to the local population. The other thing I like about this photo is to note that the treatment plant is surrounded by fields. Since then, a lot of houses have been built around it, and the residents now take great pleasure at complaining about the slightest emission that comes out of the treatment plant, which is fair enough, but I would remind them that the treatment plant was there first. So there's been a lot of interest in the last probably 10, 20 years about how we can improve the quality of that digestion, what it's doing for us. And one of the ways that people have been looking to do that is through cell lysis. Cell lysis is pretty much a straightforward process. If you look at sludge produced by a treatment plant, it's a mixture really of a number of things. Inert solids, so particles of sand and grit, bacteria that you've grown in the treatment process that have helped you to remove the soluble pollutant, remaining pathogens, bacteria that can cause human illness that are still present there, and also quite a lot of EPS or extracellular polymeric substances, which is really the slime the bacteria secrete to help them absorb those pollutant materials and treat them. And what you're looking to do with lysis really is to break all that material up and make it easier for anaerobic bacteria to use as a food source and break those cells open. And there's a number of technologies out there that can do that. The one that's probably got the most market success at the moment is thermal hydrolysis. A number of you may have heard of Cambi. Viola also have some thermal hydrolysis processes, and there are others out there as well. That's probably what's got the most in space, but there's also ultrasonics, mechanical shear, chemical reactions, I've seen people trying to do it through electrical discharges. Really anything that will break those cells open, people have been looking at. And the other thing that people have been doing to enhance digestion is to move it away from the sludge and into the mainstream. So upflow anaerobic sludge blanket reactors, particularly in warm climates, are a great solution for anaerobically treating the sludge before aeration, and anaerobic membrane bioreactors are another option to potentially generate the methane in the liquid phase rather than relying on sludge treatment. We talked a bit about the circular economy and carbon neutrality. I think it's interesting now. We've seen a few plants around the world that have managed to demonstrate they can get to net zero for energy for treatment. But now Australia is starting to regulate and demand that new treatment plants are carbon neutral. And that standard is looking at both the carbon dioxide used in the energy that's used to treat it, and also things such as methane, greenhouse gas slippage from things like methane that escape from the process. And the approach really to getting these carbon neutral plants is to look at as efficient a technology as possible for the biological treatment. Some of the things we've talked about today or other low energy treatment options. Get the maximum amount of energy recovered through digestion as possible. And often you will look to see if there's other organic waste you can import to the plant to co-digest with your sludge to increase the energy production, and potentially on-site generation through other renewables. And what's the future? Well, maybe there's other ways to use the carbon that's contained in the sewage rather than converting it into methane in anaerobic reactions. Certainly fuel cells are at the development stage, and a number of universities and others are working on how could you potentially get electricity directly out of wastewater treatment. And something else that I think is quite interesting, and I'm privileged to be on the Industrial Advisory Committee for, is a European research project that's looking at using the energy in wastewater to drive desalination. So the MICE project for microbial desalination has made some great strides and has now reached the point of building a demonstration plant. And if anybody's interested in that, you'll be able to find that on the internet. So finally, talk a little bit about nutrients. And really, the nutrient I think it's most important to talk about is phosphorus. Nitrogen is a nutrient in sewage, but there is so much nitrogen in the air that really looking to recover nitrogen from sewage at the moment, at least in my view, doesn't make a lot of sense. Whereas phosphorus is a limited resource. There's only a finite amount of phosphorus on the planet. And when we've used our way through it, we'll be in trouble. And at the moment, we're working quite industriously to take the phosphorus from the land and dump it in the sea, where it's going to become very much harder to get at as it washes off from agriculture and gets discharged out of wastewater treatment plants. Phosphorus recovery is a separate product. It's normally applied to plants that have biological phosphorus removal and anaerobic digestion. Biological phosphorus removal accumulates phosphorus within the cells that are doing the treatment. And when you put those in an anaerobic environment, they will release that phosphorus back into solution, which in your treatment plant is a real problem because it will just build up until you exceed your effluent requirement. So trying to take it out makes an awful lot of sense. Anybody who's run a biological treatment plant and with a big digester will probably know all about struvite. It's a yellowish material that will precipitate out quite happily on the inside of your pipes, the tips of your centrifuges, will form whitey yellow crystals within the sludge itself. Certainly, it's not unknown for pipes to block up to the point that digesters can't discharge and the lids the tops come off them. But what phosphorus recovery systems look to do is deliberately precipitate struvite from the either in the digested sludge or in the watering returns. And often the limiting element for struvite precipitation is magnesium. So by adding magnesium to the system, you can encourage more material to precipitate, and you can get a precipitate out that's a nice clean product that's actually a better source of phosphorus than most of the minerals that can be mined. And there's a number of companies now have phosphorus recovery systems that have been marketed, and you can see the picture there of one of the largest in the world that's been installed at Stickney, which again is something that Black Veatch was privileged to have been involved in. Now, there are some interesting things to note about phosphorus. One of them is if you've got a biological phosphorus removal plant and you don't take the phosphorus out separately from the sludge, then you actually get an interesting issue when you try to apply it as a fertilizer. If you apply biosolids to the land at the rate at which crops require for nitrogen, you'll find you're significantly over applying the phosphorus. Depending whether it's aerobic or anaerobic, the stabilization that's to be applied affects the number, but many times more phosphorus is applied than you need. So when you increase the phosphorus loading in the soil, you tend then to get wash off of that material. It can wash into the rivers and lead to eutrophication of the rivers and lakes or bays. And it's interesting, if you look around a number of major cities, you'll find that so much biosolids has been applied that they now have pretty much a total moratorium on applying biosolids because of the phosphorus flow that's been applied while they wait for that to get worked out. If you separate that phosphorus off on a struvite harvesting plant, you can get a much more balanced fertilizer, because certainly you don't want to be applying the sort of material rate that is phosphorus limited, because you'll need a much bigger land bank. And you'll also find the farmers aren't that keen on the material because they're getting very little nitrogen benefit, and they have to go and separately apply nitrogen to the field as well.
Hello.
And the other thing I hadn't realized until fairly recently.
I think you would have.
Sorry? Hadn't realized until fairly recently was the continental movement of phosphorus. So we tend to produce food in the agricultural areas in the center of continents. A lot of the cities are on the coast. Will pay to move the high use food out to the cities, but nobody wants to pay to ship sludge back again. So we're actually moving the phosphorus balance around our continents. So that's it. Hopefully we've had some look at how just LIFO is evolved from the hand crank on the wall you saw in the old movies to the handheld devices today. So we've seen something of the evolution of the wastewater treatment from really a problem to the modern integrated resource recovery facility and potentially the biorefinery of the future. I hope that was interesting. Thank you for your attention, and if anybody's got any questions, I'll see if I can answer them.
Fantastic. Great. Thanks a lot, John, for a fantastic presentation. I think that was really very informative. Happy to take on any questions. If anybody would like to ask questions directly, please unmute your switch on your video cameras and ask the question directly. If we have a question right now, we can start with that one. If not, probably John. Guys, one very common comparison happens between when somebody says that, okay, we are actually trying to build a resource recovery plant. So if we start looking at sewage treatment plants or wastewater treatment plants as resource recovery plant, then there is a very common comparison or rather, it's very natural to start comparing those processes and the economics with the conventional way of generating the same. And in that case, the argument becomes very difficult to justify. So how would you see this in the light of the changing technologies which are helping us become more efficient? And do you see that there will, at some point in time, be a significant parity between the economics of generating these minerals from wastewater as a source rather than the conventional ways of manufacturing the same?
Well, I think pretty much everything I've been talking about so far has been done by and large for economic reasons. So, and I think certainly phosphorus recovery, it isn't yet at the point that it's cheaper than mine phosphorus. I think as mine phosphorus becomes harder to get to, it could be, but really people are doing it because of the challenge that they have with the phosphorus in the biosolids and the limits they have on where they can apply it. So doing something about that and dealing with that problem, and also getting rid of the struvite problems in the treatment plants is what's driving that. Reuse, again, nobody I think is going to go for reuse if they have a readily available source of fresh water that they can use instead. But as populations grow and climate change, so there is more and more shortage of freshwater sources. And certainly when you start to look at the alternative of seawater desalination or places that aren't close to the sea, then reuse starts to become a really commercially attractive option.
Right. Yeah. Thanks for that clarification, John. I think we have Mr. BK Agarwal who would like to ask a question. Mr. BK Agarwal, if you can introduce yourself and ask your question to the speaker. Thank you.
Yeah, John, this is BK Agarwal. I work for an Indian company called Triveni. I'm president corporate here. One question to you on the phosphorus recovery. Typically, wherever you go for recovery, there is a cost, capital cost and the operating cost. I'm not asking capital cost. To make it viable, what should be the operating cost for the phosphorus recovery plant?
I'm not sure I've got any numbers off the top of my head, and you've got to be very careful what you're talking about because numbers that make sense in the US aren't going to make sense in India or elsewhere. So I'm struggling a bit to give you a number for that.
Give your number, whatever number you have.
I'm struggling to think. I'm afraid I don't have one off the top of my head. I mean, the actual operating cost is normally pretty low. It's a bit of magnesium salt. So that's our experience is the operating cost is low. It tends to be the capital cost that's the driving for. And the other thing is it is possible to get some of these systems effectively to pay for themselves with the revenue value of the product that's produced.
Okay.
Right. So thanks, Mr. VK Agarwal. I think we have a question from Shankar Ramamurthy. Shankar, would you like to unmute yourself and ask a question?
Yeah. Thank you. I hope I'm audible.
Yeah. For the benefit of everybody, you can just introduce yourself and then ask a question. Thank you.
Thank you. That was an excellent presentation, John. I'm Shankar Ramamurthy. I spent over more than 35 years in the water sector. Recently, I just moved out of Adani Group. I've been specialized only in water sector for all my career. I just saw the entire presentation and I saw it was very pleased to know that there are technologies that Black Veatch has developed with regards to various processes as well as managing the footprint, power consumption, sludge. So I only want one submission that I would like to see physical presence of these technologies implemented in India, considering that India and the sewage treatment plant sector is at the tipping point. There are huge projects of some of the capacities, some of the largest in the world, 500 MLDs, and those kind of capacities are getting grounded. So I would like to see these technologies implemented so that the benefits are derived at a city level scale, and it will be very impactful for the entire country.
Yeah, well, hopefully it'd be possible to see them. I mean, I think often it's a question of looking at what steps you need to take. Sometimes it'd be appropriate to apply these technologies straight from the beginning. Other times, if you want to get the first benefit of treatment, if that's not there at the moment, maybe something slightly simpler and then move on to it. But it's all a question of what's affordable on a large-scale treatment plant and what you're trying to achieve. But I think there's some real opportunities there. And certainly some of the biological phosphorus removal stuff, I think, has some real potential.
Thank you, John. I hope to see them applied in India.
Yeah.
Sure. Thanks, Shankar, for the question. We have a question from Avinash Shaw. He's asking, do you see value in suggestions that biosolids and municipal organic solid waste can be co-treated anaerobically?
In general, yes, I do. I think there is a lot of potential benefits for doing so, and we're seeing some opportunities. The UK has actually managed to get itself in a pretty difficult position and doesn't tend to do that, mainly because of BSE or bovine spongiform something or other. And the real issue there is that people are concerned about the presence of prions, particularly in food waste that's digested. And to deal with that, high temperature pasteurization post-digestion is required. On biosolids, there's often treatments required at the front end. And to actually get the economics of those two to work together is difficult. Elsewhere in the world, such as the US, and pretty much anywhere else, really, it's pretty common, and certainly combining digestion of multiple materials for energy generation makes an awful lot of sense. And if you look at parts of Europe now, high energy waste, such as margarine waste, are actually you have to pay to get hold of as a digester fuel. So the supplier charges you for it rather than you getting paid to treat the waste, because there is energy potential.
Right. Yep. Thanks for the clarification. There's a question from JN who's asking, is state of the art for estimating states of anaerobic digestion mature?
I'm not. Can you repeat the question? I'm not quite sure I followed it.
Right. I thought so. Jane, could you ask your question very clearly? Not sure whether the person
I mean, in terms of is digestion technology mature? Yeah, we're constantly learning, but I think conventional municipal biosolids digestion is pretty well understood now. The things that I think are much more in the development stage are the enhanced cell lysis processes, and also things like can be they are very much developing. I think they will over the next few years. And I also certainly low temperature digestion is very much an emerging technology. Some people are making advances there. The other thing I think we're seeing is things like hydrogen augmentation. So certainly there is a number of things happening that have the potential to increase energy yield and reduce volumes. We're always learning.
Yeah, yeah, right. Any other questions do we have? I think there's somebody raising. Yeah, Mr. Agarwal, you have one more question, is it? BK Agarwal, do you have another question for John?
No.
Okay. Okay, that's fine. I think somehow I'm seeing the hand raised still, so probably you just need to unraise that. Okay, do we have any other questions for John? Otherwise, probably we are already 8 minutes past our time, so we can. Okay, I think there's somebody raising hands over here. Can you just unmute yourself and ask the question, please? Please identify yourself. Abhinash Patro, can you please ask your question? Mr. Avinash Patro, you have raised your hand. Can you ask a question? You unmute yourself and ask a question. Mr. Avinash, we are not able to hear you if you're asking a question. Right, I think there's some issue of audio issue for Avinash. Do we have any other questions for John? Right. So I think with that, probably I would like to thank all the attendees who have been able to make it for this evening session today. With special thanks to John to make this presentation and give us a wonderful synopsis of what's actually going on as far as resource recovery is actually happening in relation to wastewater treatment. So thanks a lot, John, for the wonderful presentation, and I hope everybody has enjoyed and had a very good and a very informative session. Thanks a lot. You all have a good evening, and bye. See you for the next session of a civil nature organized by the Institute of Civil Engineers. Have a good evening.
Thank you very much.
Bye.
Thank you.
No problem.
Bye-bye.
Thank you very much, John.
Thank you. Thank you, John, and thank you, Rajesh.
Thank you, John.
Thank you.